Okay, here we're on section 3.5, which is using implicit differentiation to differentiate inverse trig functions. Okay, so let's start with sine inverse of x. And much like we differentiated log base a of x, the first thing that we'll start with, okay, so what we want to prove here is that f prime for sine inverse is 1 over the square root of 1 minus x squared. Okay, and so we'll prove this. Let y equal sine inverse of x. Okay, or in other words, sine of y is equal to x, okay, which sort of gives rise to this triangle. Okay, if sine of y is an angle, is x, then the hypotenuse will be 1, the opposite will be x, the adjacent will be, using Pythagorean's theorem, 1 minus x squared to the 1/2. Okay, if we differentiate both sides of this equation, we'll have, using implicit differentiation, we'll have cosine of y times y prime is equal to 1, which means that y prime is equal to 1 over cosine of y, which we've already indicated using this triangle is the square root of 1 minus x squared over 1. So there we have y prime, which, since y was already sine inverse, that's going to be f prime, is 1 over the square root of 1 minus x squared. So therefore, if we take sine inverse's derivative, we end up with 1 over the square root of 1 minus x squared. Okay. To do our cosine, you do basically the same thing. Okay, so the next fact will be, if f of x is our cosine, then f prime will be minus 1 over the square root of 1 minus x squared. Okay, so here's the proof. Let y be equal to cosine inverse of x, which then we can say from that cosine of y is x. So if we draw a triangle, if cosine of y is the angle, is x, then that means the adjacent is x, the hypotenuse is 1, which means that the opposite side is 1 minus x squared to the 1/2 power. If we differentiate both sides of this equation, we'll have negative sine of y times y prime is equal to 1, which means y prime is minus 1 over sine of y. From this triangle, sine of y is opposite over hypotenuse, and so sine of y is the square root of 1 minus x squared, so y prime therefore is 1 over the square root of 1 minus x squared, and then that negative 1 also has to go down there, so we have negative. And so therefore f prime in this case is just the minus of what the f prime was for sine inverse. So therefore cosine inverse of x, that thing's derivative, is negative 1 over the square root of 1 minus x squared. Okay. So much like the derivative of sine is positive cosine and the derivative of cosine is negative sine, here we have the derivative of arc sine is the positive one and the derivative of arc cosine is the negative one. Okay. And the last one we'll do is, we'll erase the board, the last thing that we'll do is tangent. So let f of x equal tangent inverse of x, then f prime of x, it's a little bit different, it's 1 over 1 plus x squared. Okay, so proof. It's a little bit different, but if y is tangent inverse of x, then tangent of y is x, which means if we make this triangle, the angle be y, tangents opposite over adjacent, and so that means that the hypotenuse is actually the square root of 1 plus x squared by Pythagorean's theorem. Okay, so if we differentiate both sides of this equation, we'll have secant squared of y times y prime is equal to 1, which means 1 is equal to 1 over secant squared of y, which is also cosine squared of y, 1 times y prime here. Y prime is cosine squared. Cosine is adjacent over hypotenuse, and so that's going to be 1 over the square root of 1 plus x squared, quantity squared, which is 1 over 1 plus x squared as hypothesized. So therefore f prime of x is 1 over 1 plus x squared, and thus the derivative of tangent inverse of x is 1 over 1 plus x squared. Okay, so to recap, we have the derivative of sine inverse is 1 over the square root of 1 minus x squared. The derivative of cosine inverse is negative 1 over the square root of 1 minus x squared. And the derivative of tangent inverse is 1 over 1 plus x squared. Okay, so those are those derivations. If you just want to memorize those derivatives, that's fine. Otherwise, the derivations are here for you. A nice application of implicit differentiation, much like that of the derivative of the log function. Okay, thank you.